So, um, all right. So I will be talking today, and I'm actually going to be talking about StarSound and Vox Magellan a little bit. But seeing that we have a lot of astronomers online, but then a lot of non-astronomers, and seeing that I did not write or actually develop the software myself, Jeff Hannum, who's listed on here, has, he would is much better positioned to speak to that and all the details in case you want to know about that. I chose to talk about the context in which this is used, and then give you a bunch of examples, show you the software, and give you some examples of how it works. So hopefully that's informative. And I can keep people interested. Okay, so it is data sonification, obviously, and a program. I'm an astronomer, and I study a lot of things. I'm not kind of narrow on one area, but I do study galaxies at high redshift. I study supernovae at high redshift and things, and I also study fast transients. And one of the programs that I've developed, which is now, I think, the largest collaboration in the world, it just grew to gigantic proportions, is called Deeper, Wider, Faster, which is DWF in the title there. And I'll mention that briefly because there's absolutely no way I could talk about that in this talk, but that is kind of the motivation for a lot of this work. So that's the lead in. Okay, so motivation, which we all know, this is just some numbers. There are a lot of visually impaired and blind people in the world, and roughly speaking, depending on who you ask, there's maybe 1 in 1,000 that kind of deal with science. So the numbers are large enough that you can reach a lot of people that may or may not be active in science, but would like to be. And so these are some of the questions that we asked ourselves way back in 2016. That's when we started this stuff. And so we said, okay, how many people would love to get into science, but maybe not confident or aren't able to? And how do we accommodate this? And also help our science, which of course in selfish reasons, right? And then just kind of make it more broad, because it just needs access to data, plots, things like that are needed in everyday life. And so we wanted to work in that direction. I'll kind of skip through these things. I think most of us know what data sonification is. I just pulled up a slide from our talk from a while back, but I do want to point out that you can either make specialized tools that require specialized equipment, or kind of general tools that are user-friendly. And we do the second here. So ours are just, it's something you just use your laptop and hopefully commonly used tools. Our motivation scientifically is that astronomy is big data, I guess you could say, lots of data, and especially that program I was mentioning, we have about 80 telescopes collaborating, and it's just a ton of data that comes in, and a lot of it in real time. So we have to sift through this and try to analyze things fast. We deal with transients with that program, and I do a lot of transient science, which I'll mention what that is later, but it's something that right now it's something that explodes and has a short lifetime, so you have to actually jump on things. So it adds an element of urgency to the data. And that astronomy in general is just a great platform to build data sonification, as many people here know. Okay, so there is sonification kind of naturally in the universe. This is just something that these are two black holes. It's a little I'm showing like a little movie of two black holes, and they orbit each other, and as they do, they lose energy, and that energy goes out into warping space around them, space-time around them. You get these waves of space-time, and these are gravitational waves, and then they merge together into a spinning black hole, and the waves propagate outwards after they merge. And in that process, I just took a snapshot halfway through. Once they merge, or as they're merging, the waves grow and grow in amplitude, and then once they're merged, they go away. And if you were to draw a line on those waves, you get something like that. Like if you had a line that covered those wiggles, you get a bunch of wiggles that increases in amplitude, and that's the signal. And that signal is here in the data. These are data from gravitational wave detectors. And that signal happens in just like about a half a second. And so the frequency is such that it's similar to just audible sound. I mean, so if you put that to sound, you actually get sonification. And this is just natural sonification. So let me know if this sound comes through. So that's just that's the sound of two black holes merging. Okay, so that's sonification. And there is another type of a merger, which is neutron stars that merge. And they take a little bit longer time to merge, but they also explode when they come together. They just come together, black hole, they make a very beautiful explosion. which also produces something called a gamma ray burst, which is it's a feature in a movie I'm playing is a feature that's pointing outward. And so the sound of those merging sounds like this. Okay, so maybe the last one was artistic license, but that was the last little ding was supposed to be a gamma ray burst happening afterwards. But you can hear it's a sonified version of the data. So that's what exists at least naturally out there. And of course, we want to sonify all kinds of data, but those are transients. Those are fast events. They occur only in seconds. The explosion might last hours to days for the neutron stars, but it's something that you have to jump on and get fast. And so with sonification, we can choose a bunch of things. We can say the brightness is maybe the volume, or the wavelength of some source is, it could be color for light, or it could be pitch for sound, or whatever you want to assign to it. But an interesting thing, which I'll come back to later, is that if you start getting complex with light, if you have multiple wavelengths shown at once, you just start getting white light. I mean, light doesn't work too well that way, but with sound, you get this quality or temper, this tone quality, and that's a benefit. So I'm going to talk about 4 quick things here. One is the tools StarSound and Vox Magellan that work on plots and graphs, and include things that's shown here like stereo localization, sounds, and things we want to do with them, take it to the future with 2D and 3D stuff, virtual reality and augmented reality. And we like to use them for machine learning training sets, etc. Also going to talk about a future direction, which StarSound can do and Vox Magellan will be able to do, is working with multi-parameter analysis. So you can look here, understand several to 10 or more properties in a single tone. I think that's going to really open up data analysis. Low signal to noise, which is something everyone in astronomy and I think other science fields are always pushing the limits. If you're trying to find data that is just deep in the noise, you want to reach those extremes and try to push science. That's hard, so we want to attack that with shown here. It's the cocktail party effect of sound, which I'll explain later. And lastly, if I have time, I'll just mention a little bit about citizen science we're trying to do with the DWF program. So first, StarSound. Okay, so this is StarSound. These are snapshots of it, and it's a tool that is you download, and there's a visualization window, which is over here in the left upper corner, where you'll have a 2D array, which is in this case a light curve. So it's the brightness of source over time. So x-axis is time and y-axis is brightness. And this particular source dips and then dips again. It's kind of like an eclipsing binary star. In the middle picture here, I'm showing a snapshot of StarSound where you can see several different parameters mapped. In this case, it could be the signal and an error and maybe some other parameter error array. And then there's just another snapshot of another tab that's available, which you can control different values or different things of the tool, which you have a choice of 128 musical instruments you want to choose from, in case you want the sound to be interesting. Plus, you can also just put in regular sine waves and sawtooth waves and work with their pitch and attack and loudness, duration, tremolo, stuff like that. So you can change them and work with them, which is really nice, to add a bunch of to make your data suit you best. And like one thing that I like about it is, if you're playing some data and you're in research and you try to understand the data, you really want to understand the errors. And the errors can be heard as either noise in the background gets louder with bigger errors, or softer with smaller errors, or the distortion of the signal. And that's nice because if you hear a nice clear signal, that indicates that's a low error, high signal to noise. So this is what I'm showing now is a snapshot of a flare star. So stars flare, they flare up in a matter of minutes, and there's a minute timer running at the top of the image I'm showing. And so this thing flares over a matter of, like, say, 30 minutes or so. So it's it's an image of some stars, and then one just kind of comes out of nowhere because it's there, but very, very faint, and then it bursts. And so there are stars in the universe that can get 1,000 times their brightness in a matter of minutes, which is pretty crazy. Thank God our sun isn't one of those. And but we try to detect these things and understand them. And so this tool works well because you can plot their light curve, which is I got a snapshot of StarSound again. you plot their light curve, and then this is a picture of the light curve. It's moving along, and it brightens quickly and fades away. So the image was, or the movie is silent, but now I'm going to play it with just a simple tone, just a simple sine wave tone with StarSound. Let's see if I can get it to go. Okay, so can you hear this fine? I hope that comes out across all right. Yes?
Yes, it's coming across fine.
Okay, good. And we can also use these for spectra. So in a spectrum, the x-axis could be the wavelength, and the y-axis would be the intensity. And this is a galaxy merging at high redshift. And if we wanted to determine if it had a certain feature that had an emission peak, and in the image, there's a spectrum, and it has one sharp little peak there, and that's just an emission peak we're listening for. So if we play those data, it sounds like this. So you can hear that peak. And the beauty of StarSound is that, I mean, I just have it playing at some just like fixed speed, but you can change that speed to go either really fast or slow or back and forth. You can do what you want with it. And a lot of times with Spectra, going really fast is nice because you can hear a lot. I don't know, the human ear is interesting. You can just hear those features quicker and better than kind of unless you want purposely a very careful analysis of the spectra wavelength by wavelength. So this multi-parameter analysis I want to talk about, which is actually, if I show you really quick on StarSound here, you can see there's like 12 bars here across the bottom on this picture. There are 12 bars, I think 12, I can't count them. Yeah, 12, but you can add, I guess. So these are for all different layers of parameters that you can add. Like right now, we're just doing one. And so the idea there is to work on the quality of the sound. So if I play a note, the same note, 3 times, let me tell if you can, what's the difference do you hear in these notes? So all the same note, same duration, same pitch or whatever, but it's different instruments, and you can identify them quickly because of the different sound characteristics. That's because they play a fundamental frequency, but the instrument produces these overtones of these harmonics that come off of it. And if you look at that in a intensity plot shown here, this is just for like a 1 second. I'm showing 2 plots on the screen with 1 second durations. And there are these color-coded strips going across that indicate the intensity of the different harmonics. So the fundamental tone is at the bottom, and then there's about, I don't know, 12 harmonics or so going up. And if it's red, it's very intense, and if it's blue, it's not, et cetera, because there's an intensity scale here. And one of them is for bass clarinet, which is a kind of a woody sound, and one is for a trombone, which is more brassy. And the overtones are very different. For the clarinet, like the 2nd and 4th and 6th are strong, kind of every even number. And for the trombone, it's just kind of the first 2, and then it fades away. And their sounds are definitely different, as we know. Here's a clarinet. And then a trombone. So that difference in sound is something we want to try to explore, because if you can imagine, if you want to look at 10 properties at once, each one of these overtones could be assigned a scaled normalized property strength, and therefore each one would have a certain strength, and objects with a certain property that you want will have a certain quality of sound. And it takes training, but if you hear the ones you want, you can instantly in one tone know all of these properties and start to be able to sort and work with data quickly and try to understand an interrelationship between the properties. And Gary is working on this. So, and this is just the StarSound picture again, where these tools, these different overtones can be built on. The second one, since I don't want to take too long, is Vox Magellan, which I think is a fantastic tool. And this is a tool to look at 2D plots and actual images. And so this is a touch-sensitive plotting tool, and it's designed such that you give it an ASCII file essentially, and it'll update data, and it plots that. When you go to plot those data, it scales it to the size of your trackpad. And so your trackpad becomes the plot, the edges of the plot. So by just feeling the edges of your trackpad, you know where you are on the plot. So you can feel around, and also then you can just touch wherever you want on the plot, and that's going to produce those sounds. So you can, it helps you envision what's there on the plot. Here there's plotted just, this is very arbitrary. It's actually a bunch of galaxies, but it's, you know, galaxies with 3 different properties. They have 3 different colors on here. So there's a whole bunch of data points, kind of a scatter plot. And the different colors represent just different classifications. But we've assigned just some random sound to them, something very distinct in this case. And I also want to explain that we will play some overtones to that. So firstly, as I mentioned, it scales to your trackpad. So like when you bring up the image, it looks like this, and then, you know, there's your trackpad. So I'm touching here, and that's right here on the, if you can see on this image is where you are on the plot. And so when I play this, it's going to play, it's just a little recording of it playing and touching the different points, but then it also changes halfway through where we add an overtone to add an extra piece element of information. And this overtone, this harmonic or whatever, will provide extra information. All right, let me play this. So it's kind of obviously like a bell sound for these. This is the second, and that's the third. So those are the 3 types of galaxies. And so just feeling around on the plot, you can kind of get a sense of where they are. And then if you turn on an overtone to get another property for those galaxies, you can hear 2 things at once, which is being set now. And then if you just have the overtone only, you can hear that one, that property change as you move around. You're moving around on the plot. So that's pretty nice way, I think, of analyzing these data. And the last example I want to show you is that it can be used for things called IFU spectra, or images in this context. And what integral field unit spectrograph is one that takes the spectrum, like a regular spectrum, but it's actually, you're taking an image, and each pixel, you can think of that as in a spectrum itself. So it's like a 3D data cube. So you have an image that has pixels, and each pixel is a spectrum, which gives you a 3rd dimension. But if you collapse that whole thing, that 3D data cube into 2, you basically just get a pixelated image, and that's what's shown here on the screen. So on the top here, there's the galaxy with the Hubble Space Telescope image, so it's just some distant tiny galaxy. And then the IFU spectra are shown next to that in measuring different properties, ones in specific H-alpha line and other velocity plots. And there's some plots there, but the tool in this case is looking at one of the spectra. And what we've done is wherever the galaxy is has some data, and wherever there isn't the galaxy is just black and no data. And the pixels are color coded on their velocity toward or away from you. So this galaxy is turning, and if it's turning toward you, that's going to have a higher pitch. If it's turning away from you, that's going to be a lower pitch, kind of like a Doppler shift when you hear an ambulance come by, right? It's a lower pitch and then changes to a higher pitch when it passes. But it's the same tool where you bring up the image, and then it scales it to the trackpad. And so you move around on the trackpad to just analyze this image. So when I play this, the first thing is going to be played is that the person analyzing this is moving around on the trackpad just to find where is the galaxy on the trackpad. And so they move around, they can kind of feel the edges. Once they hear sound, they know that's it, and they can get a sense of the shape. And then the second goal is that they're going to try to find what the rotation axis is, like which way is it rotating. So if it's like, what can be seen on the image is that it's rotating at about a 45-degree angle, counterclockwise, I guess, such that blue would be coming towards you and red going away. But they want to try to find which axis that is, so the largest change in sound. So let me play that. So they're making different cuts, and this is a cut going across, and they can hear low to high. And after multiple different cuts, you realize that you got the rotation axis. All right, sorry about that delay there. So anyway, these are just different tools and different examples of the tools in action. And so you can do a bunch of science with that. And I'll just mention that that DWF program that I mentioned in the beginning is very complex. There's lots and lots of telescopes as shown here on this Earth that operate, and a lot of them at the same time that produces these fast transients. And what we do, I won't go about the process here, but it's about, and within about a couple of minutes, we take the data and actually have to analyze it and trigger telescopes in this room here, which is a big room where everybody gets together using fancy tools and visualization stuff. But we want to add sonification. This is a web tool. Sorry, no, this is a web tool that everyone can access. Everyone here and around the world can. I'll give you the link. This is access to the tool as the data comes in live off the sky. You get images of the data, different images of it before, during, like this is an old one, a new one, and this is a subtraction showing a transient, the light curve. All these things change every minute, are updated. There are hundreds of these we go through. And so the idea is that there's a lot of visual stuff here, and we take this tool, and you can animate the images, which gets done, which is like silent movies, but now we want to add sound, and we actually want to use like 3D virtual reality and augmented reality to make it much more impactful, and we can verify the data better. So I will end there. Sorry for going long, and thanks. Take any questions.